All right, our next presentation is from Job Snyders from NTT.
Good afternoon, NANOG. My name is Job Snyders. I work for NTT Communications. Over the last 12 months, we've spent considerable effort in increasing or decreasing the amount of route leaks or partial route leaks that pass through our network. And in this presentation, I would like to go over the particular method we've used and encourage you to copy this method and implement it in your own networks as well. I've split this out in two parts. Part one focuses specifically on preventing route leaks. Part two is a routing policy update that will deploy end of June that might be of interest to you. How many of you know this particular website that Jared Moch made roughly 10 years ago? This website also has an alerter service, and for the past 10 years, this alerter service has been emailing messages out to NTT staff highlighting, hey, yet another small route leak happened. Each of these alerts contains a set of prefixes that are being leaked and the AS path that doesn't make sense. When it comes to AS paths that doesn't make sense, if you look at these big networks, a lot of them are so-called self-proclaimed transit-free networks or tier 1 networks. And following that definition, we should never see 3 of these in the same AS path because by their own definition, they are without transit. So if we see 3 of these networks in a row, clearly one is providing transit to one of the others. And when this happens, this is usually a mistake. If we plot this type of activity out over the last 10 years, this graph is very non-scientific. It is heavily biased towards the Western civilization because of the data sources used. We see that this is an ongoing issue that does not go away by itself. We need to put in some actions, put in filters to prevent these leaks. And I've highlighted 2 of the interesting cases. The y-axis is the amount of unique prefixes seen per month. And this graph shows that there's a lot of small leakage. These are not full routing tables that are propagated. These are tens or maybe hundreds of routes that are leaked for a brief moment of time, and then for whatever reason they disappear again. If we plot this type of leakage out over on which days of the week they happen, there's a very interesting pattern that clearly shows that during the work week from Monday to Friday, there is far more route leaking or small route leaking than there is in the weekends. I think one valid way of addressing this problem would be to move all maintenances from Friday to the Saturday, because this graph clearly shows that there are less route leaks on Saturdays. I'll cover various methods of trying to mitigate these route leaks, but one of the simplest methods that you as a network operator can apply is something we'll call Peerlock Lite, or the big networks filter. For a lot of people in this room, the chances of them ever signing up one of these big networks as a transit customer are relatively low. So if you implement a filter like this on all your customer-facing sessions, then if your transit customer, for whatever reason, accidentally leaks a full table towards you, this filter will at least dampen the amount of cruft you might receive. And I expect this list to be relatively static. It would be something that you might need to revisit once a year or once every 2 years. So this is very low-hanging fruit. Other low-hanging fruit is to ensure that if you receive routes from a party, you always tag them with a specific BGP community identifying to which other networks they should be propagated. So in other words, if in all your eBGP outbound policies, you ensure that you will only ever let routes pass the filter if they contain the appropriate BGP communities, and if they do not contain any BGP communities, just ignore them and not let them pass the filter. And this type of approach helps against the scenario where you configure a BGP session, but because of iOS, you cannot copy-paste fast enough, and the session comes up while you're still copy-pasting the full configuration. That type of activity is at least more controllable if you take this approach. Another approach is to apply a whitelist of prefixes that every customer may announce to you. This is easier said than done. For a lot of networks, it is still a challenge to do this in a programmatic way on a daily basis. So how you do this is a little bit outside the scope of this document. But having a whitelist of prefixes mitigates a lot of risk. However, one of the downsides of this approach is that some people put basically the entire internet in their AS set, and then the filter expands to allow anything, and then if a route leak occurs, the chances of a piece of that route leak being allowed through this filter is significant. So this is not perfect, but if you combine them with the other approaches, then we're slowly getting somewhere. And this one is super cheap. Use maximum prefix settings on all your eBGP sessions. This is one of the quickest lines of defense against unfortunate accidents. So now we'll dive into the more advanced topic of this presentation. Some of you might argue that this is old wine in new bags. That is partially true. However, I think that peer locking, as we describe it here, is relatively new to seek explicit consent between the parties involved, and the level of regional granularity, I think, is also a new approach. Peer locking, in a nutshell, is that you ask your peers, who are your upstreams? And maybe your peer says, I have no upstreams. That is valid. Or maybe your peer says, these two networks are valid upstreams. These two networks are the only authorized intermediate networks that can exist between our two autonomous systems. In this particular example, AT&T and PCW have both agreed to this peer locking mechanism, and they have both indicated that there are no valid intermediate networks between NTT and PCW and NTT and AT&T. So the example AS path that we see below, where we see AT&T behind PCW, is by the admission of AT&T an incorrect path that should never exist. And therefore, we should block it on our eBGP border. We don't use any market knowledge or computerized tools to figure out who the allowed upstreams are. We simply email peers and ask them, and whatever they say, we believe. A high-level overview that shows this system. In the center, the white circle, that's NTT. There's a blue circle that represents the protected ASN, and there's a green circle that is an example of an authorized upstream. And what the peer locking schematics allow you to define is that on the direct adjacency between the blue circle and the white circle, that is a valid path to reach that ASN. The blue circle told us, hey, via green, you can also reach us. And this is useful because maybe the peering sessions go down for whatever reason, and then we don't want to partition the internet. It is good to have alternative paths. And the blue circle has all the discretion to indicate to us who that authorized intermediate network is. So those two paths are valid, and then the rest of the scenario, for instance, seeing network A, or the blue circle, behind the red circle, peer C, that is then invalid because blue told us that. And this is what we implement on all our eBGP sessions. So again, an example is these filters prevent us from learning any routes which have 7018 anywhere in the S path except on the direct sessions with 7018 itself. The peer locking mechanism also provides for a way to say, for instance, according to some data, PCW uses level 3 to reach certain parts of the internet. In this system, you could allow for that. The peer can tell you the direct sessions are valid, or this intermediate network is valid, and a system that accommodates for all those types of cases, that is one that is useful in this world. So if you look at deploying and managing a mechanism like peer lock, I think it's very important to ensure that you apply these filters on every single eBGP session in the network, no exceptions. If you limit this to, for instance, just your customers, then any peer can still do a small or partial route leak, and you would accept it. So make it consistent across the board, apply it everywhere. Peer locking, because of, it could be that on a yearly basis, business relations between network change, because a network might be purchasing upstream services from this network today, and maybe next year they have someone else, or maybe they have a temporary transit because there is a natural disaster in some region and they just had to get capacity from whoever they could buy it. So unlike the big networks filter that we covered earlier, or peer lock light, this iteration of the concept, I consider it very dynamic, and make sure that you have, if you implement this, have a system that can be updated within, say, minutes rather than days. And because of the dynamics in this world, the way people buy peering or buy transit, and those policies might differ from region to region, it is very useful if you already built into your system a sort of understanding where you can whitelist particular things in a specific region rather than have everything be a global setting. And then the last point about managing peer lock, it is very important that you do this with the consent of your peer. Because if you apply a filter on all your eBGP sessions that prevents any other intermediate network from propagating your peer's routes to you, and maybe at some point you have a dispute or the relationship ends, but you don't have those filters in, and you have those filters in place, but your peer is not aware of those filters, you might end up with a small partitioning of the internet. But if both parties are in the know that this type of filter is in place, then both parties can plan accordingly and request changes from each other. This is a small mock-up of what our internal system looked like. For peer locking, we consider each row in the table a rule. And the rules specify what is allowed, and so that's a sort of whitelist, and then the default is to blacklist the rest. So if we go over these examples, the first one I mentioned, PCW, they told us that there should be no other networks between us and PCW. So we've set allowed upstream to none. There is no other network that is allowed to propagate those routes to us. This applies globally in every region where we have peering sessions. You see the ignore constraints column. I'll cover that in a second. But it's in this case false because we're not ignoring any constraints. And the rule is active. It's deployed in the network. Every time we generate configs, that will be part of it. And through this mechanism of rules, we can pretty granularly specify what is allowed in which region. About those rules, the rule constraints, as we implemented them, are a programmatically verifiable suggestion to the human operators about whether a peer lock rule is something that is good or whether it's a risk or liability to break parts of the internet. Every BGP session that exists in our network exists in the database, and with these constraints that can be expressed in, say, a simple script, we can constantly validate whether what is configured in the network and what we try to enforce as policy, whether that is still reasonable or something might be at risk. As an example, the first constraint is that both the protected ASN, the network whose ASN we are blocking on all eBGP sessions, except the ones where it is allowed, and allowed upstreams, the networks that were authorized by the protected ASN to be an intermediate, they must be directly connected to the NTT network. If they are not directly connected, then those rules and policies could have very adverse effects. To further reduce risk, we only allow networks to fulfill the role of allowed upstream if we connect with them in multiple regions. This helps protect against natural disaster. But this constraint might not be applicable for everybody. There are plenty of networks that do not operate in multiple continents, but focus on a smaller area. So with all of these constraints, I recommend that you assess them individually and verify if they make sense in your network or not. And for instance, the last constraint is also one that can easily be overlooked when you're clicking in a web interface and adding new rules. You can only specify that there is an allowed upstream for a region if that allowed upstream actually connects with you in that region. Because if there is no BGP session within that region, then it's weird to whitelist them for a specific region. If you want to toy with this concept, I put a script on GitHub. This is not our actual implementation. This is just a sort of proof of concept script that you can modify and toy with. If you look at the contents of the Python script, you can see two dictionaries that are defined. Those should be replaced with a connector to your own database, assuming that you have stored all your BGP sessions in a database. But if you change those dictionaries, you can see what type of filters come out, and you can try and modify the script to accommodate for your own network with your own naming scheme and your own BGP sessions. A small warning, this really is a proof of concept script, so don't try and jam it into your production network tonight. Use it as an example, and please just redo it with whatever logic is applicable for your network. If we look at examples that come out of this type of program combined with the peer lock rules, for instance, the above AS set is applied on all the eBGP sessions we have with AT&T, and you can see that there are quite some big networks that are matched in that particular AS path set, and in our policies, these sets are referenced with a very simple, if this matches, then block the route. The example script that I provided and put on GitHub, it generates configs for iOS, XR, and Junos. And below is an example how we match this on Junos. If you want to somehow get peer lock in your network, the way we implemented it is that our peering team reaches out to peers and says, hey, look, we have this special type of filter. Are you interested in this? We provide them with technical documentation that shows configuration examples of what would be configured on our side of the link, and then their engineering teams can assess whether they agree with that or not. If the peer agrees that enabling peer lock is a good thing, we have a sort of due diligence step in which NTT's engineering team assesses whether it makes sense. Because maybe the peer says, well, this, and this network would be authorized intermediate networks. And maybe there's a typo in one of the ASNs. So our engineering team has to scrutinize whatever information we receive from the peer to see if it would break the internet or not. Once there's agreement on what the rule set should be, we move forward. We coordinate with the peer, look, at this and this moment we'll deploy the filters. The operational impact of such a deployment is always zero, or should be zero, because peer locking is merely to accommodate what should be there and protect against accidental route leaks. And during the moment of deployment, usually the route leaks are not always ongoing. So when you deploy this, there should be no adverse effects. The peers can always contact the NOC. Our NOC is committed to provide them with timely responses. We understand that there might be situations in which the rule set should change within a matter of hours, and we are committed to accommodate those short time windows. If we would be putting this on the slow track and taking days to deal with requests, then we would fail to meet the expectations of reality. This is the manual we email to peers. Again, feel free to copy paste it, modify it, change it, or just read it for your enjoyment. The documentation contains examples because we've noticed that there might be language barriers between us and peering partners, but if there's anything universal, it is Junos configuration. So by providing them the configs, it is much easier to explain what's going on our side. There's a bit of a disclaimer. We highlight what element in this system has what name and what does it mean, and of course how to request changes to the rule set. This concludes the peer locking part. We'll now dive into the second part of this presentation, and that is about bogan ASNs. Many of you might have seen the announcement on the NANOG mailing list. I've tried my best to distribute the policy announcement to as many people as possible. But what it boils down to is that because our equipment is 4-byte ASN capable, we should never see AS23456 anywhere in the AS path. They should be hidden from us because we support proper 4-byte ASNs. So the occurrences that we do see of these bogan ASNs are either software defects somewhere in a router implementation, or they are misconfigurations. And neither of those should be rewarded by accepting those routes that contain the 23456 ASN. And a similar philosophy applies to private ASNs. Private ASNs have no place in the public default-free zone. And as such, we will block any routes that contain private ASNs anywhere in the AS path. The new paradigm essentially is to fill fast and fill hard to encourage people to configure their equipment correctly. Because if you are busy configuring the router and you notice that your reachability is limited, you are incentivized to research why there is limited reachability. And then you might discover, there's a private ASN somewhere in the AS path. But if we accept these routes, you never have any incentive to fix the configuration. We are not the only ones that will deploy this policy in June. The following have committed in public to deploy a similar policy. GTT, AT&T, and KPN will deploy this in a similar time frame. And DKIX on their route servers have committed to this filter as well. So it is very encouraging to see that we're not the only ones that try to clean up the public routing tables, but that there are more companies like-minded. This is a list of the bogans we'll drop. 0, that's an invalid ASN. 2, 3, 4, 5, 6, that's the transitional ASN for 4-byte ASNs. And then there's a bunch of private ASNs and documentation ASNs that should never be in the routing tables. At the below URL, you can always see the latest list that we are blocking at our eBGP border. If you go to this URL, you will see various configuration examples that you can copy-paste into your own network for iOS XR, Junos, and BERT. And there is also an example for iOS, but I highly recommend against using that one because it is one ugly beast of a regular expression that is unreadable, undecipherable. So that's more there for your entertainment than for production values. But the one for XR and Junos and BERT, those are things you can copy-paste and put in your network. Part 3 is a quick overview of how a route gets into our network or leaves our network. Step 1, or protection layer 1, is maximum prefix. On all the eBGP sessions, we have maximum prefix settings, and on a daily basis, those are automatically corrected for growth, organic growth that a peer might have. So this way, we, as humans, rarely have to touch them, because if a network steadily grows over the months or years, the system will just follow that. Step 2 is that we reject bogan prefixes. Bogan prefixes are, for instance, RFC 1918 space. Step 3 is the policy that I explained just before, the bogan ASNs. In step 4, we reject prefixes that are used as peering LAN prefixes. It might not be desirable to accept a more specific for a peering LAN prefix. This has been extensively covered on the NANOG mailing list multiple times. Just be sure to have this in your inbound policies. Step 5 is the route lock, the peer lock filter. It's an AS path-based filter. It's the same filter as used for V4 and V6. Then next is a match against a whitelist of prefixes that we derive from the IRR systems. Then finally at step 7, we stop purely matching and then deciding to accept or drop, but we're actually doing something with the route. We will mark the route as a, for instance, customer route if it's a customer session, or a peering route if it's a peering session. We remove some communities that should only exist within our internal routing domain to prevent accidental features from being used. And then finally, the route is going through some logic that does stuff like black holing or selective black holing or local preference modifications. On egress, we have a similar but not entirely similar system. First step is to remove prefixes that we should never announce, such as RFC 1918 space. We set remove private ASN on all eBGP sessions because internally we use private ASNs a lot for our confederations, but they should never leak out to the public internet. We have a step in which arbitrary bad routes can be blocked. Sometimes there are prefixes on the internet that carry strange attributes that pose a security risk for some implementations, and that would be the place where we block such prefixes. Then there's a little bit of logic that if the route that is going through the filter, if it matches the peer BGP community, it can be announced to a customer. And on all other sessions, we will always announce the customer routes. There's a step for logic to apply the requested features. For instance, prepend 5 times in this region, or prepend 2 times towards that peering network. Again, we rewrite some of our internally significant communities, or we delete them. We set next stop self, we normalize METs, and the route goes out of the filter. And anything that does not match the the requirements is just dropped on the floor. So for instance, if the route does not have any BGP communities, we will never announce it to eBGP neighbors. This concludes my presentation. If you want to follow up with me or have questions about the Python script I put on GitHub or about the documentation manual that was linked earlier, you can always email me. I'd be happy to help our competitors implement this mechanism as well. And any of the networks that I mentioned in this presentation may or may not exist in reality. All right, question time.
Matt Petak, Yahoo. So in this nicely automated thing, you still have the email process as kind of one of the core aspects of this. Are you?
It's better than faxing.
It's better than faxing, I will grant you that. No arguments there. Are you authenticating who's sending these? Do you just kind of, somebody emails you knock and says, yeah, I'm from AT&T and you need to start accepting 3356 is our downstream now. Okay, thanks. Does your knock just execute that? Is there some filter of only accept email from these people? How do you actually make sure that this doesn't turn into an attack vector?
In one of the earlier slides, I referred to it as the human network. Our peering team has personal relations with or other peers, and it is from them that we accept changes. So
a new hire is treated as you're scum until I know you?
Yeah, we asking the people that we know, like, hey, does this guy actually represent you, or is he authorized to request this type of changes? But it really depends highly on the personal relations that we have.
Any thoughts of how that might scale better, or do we gonna have the super secret handshake club where we all exchange okay, use the shibboleth keyword when you email, and then we'll all know it's okay to do the update?
As you know, skill is always a problem for later. But you are right. I'd be very interested. So now that we have this in place, and it took us a while to develop it, so far it seems to scale for us, but our peering profile might be very different than that of some people in this room. And if you're dealing with tens, it's easy, but if you're dealing with thousands, I can imagine it being a high burden. So maybe we should have a central location like peering the B, where people can say, I have authorized upstreams or not, or maybe some other central location that is accepted by the community. I'd be willing to further research things like that to make the process more scalable.
Hey, Vikas from Microsoft Core Operations. So basically we use all of these techniques except the IRR whitelist. I may not be aware of it. But the point is, how is it relating to the prefix hijack? So let's say if you are my upstream, you have to implement it on all of your BGP peers, similar thing, to avoid getting my prefix from someone else and then sending it out, right? Because if we both are doing the peer handshake thing, then I am avoiding, so basically what we do for it is to avoid someone else to become transit. If he's directly peering with us, we don't want that prefix to come from a transit provider. So that's where we drop it. I'm trying to understand how it relates to the route hijack, because that is upstream ISP getting a prefix I own from someone else and then sending it out, right? So for that, my upstream ISP has to do it for every of his BGP peering, same thing that he's doing with me, correct?
This mechanism was not designed as a measure against hijacking. This is purely to protect against accidental route leaks. So the scope that we try to address with this is different. And if we want to protect against hijacks, that is a very different problem space with very different characteristics.
Joe Provo, Google. Wow, booming, awesome. Hey, yo. In reverse order, to address Mr. Petak's question of scale, investigate a portal that you could expose to your direct peers. I think a large entity does that.
Sorry, I couldn't hear you.
Investigate deploying a portal for self-service for your peers to manage such things. Therefore, if there's a garbage in problem, they gave it to you. In terms of the ingress and egress policy, thank you for documenting good practice. I think a lot of people in this room have been doing them for quite some time, but it's rare to actually see a good, solid compilation. So thank you. With respect to bogons, I'm really curious how many people haven't been doing this.
I think quite a number. Let's see if there's a back button. There we go. I've noticed that the traditional 16-bit ASNs, they generally don't make it very far on the internet. But when the 4-byte private ASNs, the, 4,200 billion up to some other number, when that was introduced, I think a lot of people overlooked that they were now private ASNs. And so a lot of people do a bogon ASN filter in some form. And what I'm encouraging people to do is to use this specific list, because this list is now up to date and appropriate according to IETF standards.
Yeah, I've been concerned when I've seen people actually advocate using built-in vendor knobs, because once such specifications change, you will not be tracking reality. So yes, I agree. Thank you very much. And back to the original, I think it is old wine, but in a much, much better bottle that scales and is more automated. So thank you for the update there. It is a valid point that I think you missed one benefit. Certain forms of AS path forgery are then eliminated using this method.
Absolutely.
And actually, going back to like slide 4 or something, when you had the graph of source ASNs, 3549 before it got bought by 3356 had no.
This one?
No, go back. The pretty colors, that one. They had no community-based TE and actually encouraged their customers to perform AS path forgery. So that's where some of that data may be coming from.
Yeah, I was looking at this data and I had trouble placing it in historical context, because obviously this graph goes from 2008 up to 2016. And in 2008, I was still walking around in diapers and wooden clogs. So but thank you for sharing that nugget of wisdom. Any other questions?
Thomas King from DKIX. What is the prize I can win if I find a bug?
I'll have to think about it. How about a /24 of RFC 1918 space? Thank you.
All right, thank you, Joe.